This is the section 9.7 video. So in this section, we're going to learn about methods of maximum likelihood. And so the goal is to find the best estimator, in other words, an estimator that is MVUE. So we've discussed a couple different procedures up to this point. We've saw that we could find a minimally sufficient statistic, which is unbiased, and that'll get us the MVUE. But the problem with this is guessing what function we need to use to get to the MVUE. We could use the method of moments, which is straightforward, and it usually gives us consistent estimators, but it doesn't necessarily give us MVUEs. And then, so the next one we're going to look at is the method of maximum likelihood, which will often lead to MVUEs. All right, so kind of as an example to lead off in this topic, suppose I have a box that contains 4 balls, all of which are either white or red. And we're going to select 2 balls without replacement, and exactly one of the selected balls is red. So in other words, y is equal to 1. And what we're going to do is we're going to estimate the number r of red balls in the box. So notice the following. We know that r, which is the number of red balls in the box, has to be equal to 1, 2, or 3. And the reason that we know it can't be 4 is we know that all of the balls are either red or they are white. And since we have 2 balls in our sample, notice that 1 was red and 1 was white. We know that r can only be 1, 2, or 3. Because again, we know at least one of them is white based on our sample that we found. So notice, if r is equal to 1, so let's suppose out of the 4 balls in the box, only one of them is red. Then the probability that y is equal to 1, so in other words, we draw 1 red ball, is equal to, out of the red balls, we choose the 1. Out of the 3 white balls, we choose 1. Out of the total ways to choose 2 from the 4 balls, and this is equal to 3 over 6. On the other hand, let's suppose there were 2 red balls in the box. Then the probability that we draw 2 red balls the probability that we choose 1 red ball is equal to the following. Out of the 2 red balls, we choose 1. Out of the 2 white balls, we choose 1, divided by the total ways to choose 2 from the 4, which is equal to 4 over 6. And then finally, let's suppose that there were 3 red balls in the box. Then the probability that we only draw 1 red one is going to be equal to, well, out of the 3 red balls, we chose 1. Out of the 1 white ball, we chose the 1 white ball. And then out of the 4 total balls, the different ways that we could choose 2 is equal to 3 over 6. So again, what we're trying to figure out here is how many red balls are in the box. We drew 2, only one of them was equal to a red ball, or only one of them was red, I should say. So what we're doing here is we're looking at the different possibilities for the number of red balls that are in the box, and then further looking at the probability that we only got 1 red ball when we chose 2, and those are these different probabilities. Since we observe y is equal to 1 is more likely if r is equal to 2, then we estimate r hat is equal to 2. So again, we looked at all the different possible values that r could take, and for each of those scenarios, we looked at the probability of drawing 1 red ball. We see that the probability is highest when r is equal to 2, so that is going to be our best estimate of 2. In other words, we have maximize the likelihood in this case. Now this is for a discrete distribution. We're going to focus on how to do this with other discrete distributions, but also with continuous distributions. So looking at our definition here, the method of maximum likelihood estimates theta 1 through theta k. So we can estimate multiple parameters here by choosing values theta hat 1 through theta hat k, which maximize the likelihood. So suppose that y1 through yn are discrete random variables. Then remember that the likelihood is going to be equal to the probability of observing all the different outcomes that we observed in our sample. So maximizing the likelihood function is the same thing as maximizing the probability of obtaining the data we observed, which is exactly what we did in that previous example we just saw. So let's look at another example. We're going to let y1 through yn be IID binomial, and we observe y1 through yn. In other words, we've got a sample of n observations. And we're going to find the maximum likelihood estimator of p. Now, we already found previously in the notes the likelihood function for p. So let's write that down. Well, L of p, just using this notation right here, that's equal to the likelihood function. And we've shown previously for that binomial, this is equal to the following. And we can say that this is equal to p to the y, 1 minus p to the n minus y, where little y is equal to the sum of the yi. All right, so what we need to do is we need to find the value of p which maximizes this function. Right? Now, one way we could do this is we could take the derivative and set it equal to 0, but notice that this is difficult based on the format of this function. So instead, what we typically do is we look at the function, the natural log function, which is strictly increasing. So we can maximize the natural log, and that's the same thing as maximizing the function. So writing that down, and we call this the log likelihood. In general, when you're working with method of maximum likelihood, you're usually going to maximize the log likelihood, which is, again, the natural log of the likelihood function. So notice in this case, if we find the natural log here, we're going to have the natural log of L of p. Well, that's going to be equal to the natural log, and I'm just going to plug in what L of p here is. And the reason taking the log is nice is we no longer have to worry about the multiplication. It's going to change it so we get to work with where it's additive. And so this is equal to y natural log of p plus n minus y times the natural log of 1 minus p. And so again, the reason we do this is because of this. And again, the reason we want to be able to differentiate, because our whole goal here is to maximize the function. And remember, you can do that by taking the derivative and setting equal to 0. And we're going to do just that. So we're going to take the derivative of the log likelihood with respect to the parameter we're trying to maximize. So be careful here. This is going to be that derivative with respect to the parameter that we're trying to estimate. And so notice this is equal to y over p plus n minus y over 1 minus p times minus 1. And what we're going to do is we're going to set this equal to 0, and then we're going to solve for p, and that's going to give us our estimator. All right, so if we do this, since I'm setting this equal to 0, what I'm going to do is I'm going to replace my p's now with p hats. So I've got y divided by p hat plus n minus y times 1 minus p hat times negative 1 is equal to 0. And again, it's because I'm setting it equal to 0, I'm now going to call it p hat. Well, this suggests that y divided by p hat is equal to n minus y divided by 1 minus p hat. Therefore, we get y times 1 minus p hat is equal to p hat times n minus y, which in turn suggests that y minus y times p hat is equal to p hat times n minus p hat y. And then y is equal to p hat over n, and therefore p hat is equal to y over n. And remember that the y we have here is the sum of the yi's. So the MLE is p hat, which is equal to y over n. And remember, we already showed that this was MVUE back in earlier sections. All right, the next one is one that I would like you to try on your own, and that'll be the quiz for this section. And so just some kind of steps that you'll need. So we already found the likelihood function. Move that down for you. And we found this in an earlier section. All right, so the steps that you're going to need to do to find the MLE. Step 1, you're going to find the log likelihood. In other words, you're going to take the natural log of L of theta. Okay. Step 2, you're going to set, step 2, Step 2, you're going to find the derivative of natural log L of theta with respect to theta. And then step 3, you're going to set that derivative that you found equal to 0. And then once we set it equal to 0, what we're going to do notationally is you replace theta with theta hat. In other words, the notation for the estimator, because once we set it equal to 0, we're looking at a specific instance. And then step 4, you're going to solve, that's not how you spell solve, you're going to solve for theta hat. And that's how you'll find the MLE. And what you should find is that the MLE is equal to y bar, which again we already showed was MVUE in the previous notes. All right. Next, we're going to find the MLE for a normal distribution. And we're going to do this both for mu and for sigma squared. So again, the first thing we're going to do is write down the likelihood function. Should be given mu sigma squared, and we found that that was equal to the following. So there's our likelihood, and we're going to follow the exact same steps we did before. So the first thing we're going to do is find the log likelihood. Notice here I've got two parameters, so the function is going to have two parameters, and that's going to be equal to the following. Simplifying this. So now we can go through and we can find the MLE for mu and for sigma squared. And we're going to do that in two separate steps. So first, we're going to find the MLE for mu. Now, my very first step is I'm going to take the derivative of the log likelihood with respect to mu. Notice when I do this, the first two terms do not contain mu, so that's just going to be 0 plus 0. And then taking the derivative of this term with respect to mu, I'm going to have the following. All right. Now, just like before, I'm going to set that derivative equal to 0. And notice when I do that, these two terms, since they're constant, if I multiply both sides by a constant, the 0 side is still going to be 0. And so that's just going to leave me with this term right here. So let's do that fully so you can see that. So what I'm going to do, I'm going to have 1 over 2 sigma squared. Well, I've got 2 there, so those are going to end up canceling. Times the sum, I equals 1 to n, yi. Now, I'm going to be estimating mu, so I'm going to put a hat over top of it, so I've set that equal to 0. And this was what I was saying. Notice this is just a constant now. Multiply both sides by it, and I just end up with the sum I equals 1 to n, yi minus mu hat is equal to 0. So first taking the sum through here, I'm going to have the sum I equals 1 to n yi minus n mu hat is equal to 0. And next, this is going to give me that n mu hat is equal to the sum I equals 1 to n yi, and therefore mu hat is equal to the sum I equals 1 to n yi divided by n. And notice that is y bar. That's the sample mean, and that's generally what we would expect to happen. So now we're going to do the same thing, but now we're going to find the MLE for sigma squared. So again, the very first thing I need to do is take the derivative of the log likelihood, but this time it's going to be with respect to sigma squared. So to rewrite this, so let's mark this line out and rewrite that. Alright, so again, we'd already found that the natural log of the likelihood is the following. And so that's equal to negative n, natural log of sigma, minus n, natural log of 2 pi, square root of 2 pi, minus 1 over 2 sigma squared times the sum I equals 1 to n yi minus mu squared. Alright, so notice here we're going to be taking the derivative with respect to sigma squared, and that can get a little confusing. So what we're going to do is we want to rewrite these terms that have sigma squared. We want them both to be in terms of sigma squared. So notice this term right here, what I could do is that's equal to 2 over 2 n natural log of sigma. Of sigma. So just rewriting out the other terms. Now, using my log rules, since this is multiplied by 2, I could have sigma squared here. And so notice this is equal to negative n over 2 natural log of sigma squared minus n natural log of the square root of 2 pi minus 1 over 2 sigma squared, the sum I equals 1 to n yi minus mu squared. So now that my terms that have sigma are both in terms of sigma squared, what I can do is I can do a little bit of substitution to make it easier for me when I go to take the derivative. And so what I'm going to do is I'm going to let theta be equal to sigma squared. And so that's going to give me the log likelihood of mu and theta is equal to the following. I'm going to have negative n over 2 natural log of theta minus n natural log again square root of 2 pi minus 1 over 2 theta times the sum I equals 1 to n yi minus mu squared. Then next what we can do is we can take the derivative of the log likelihood, of mu theta with respect to theta. And that's going to give us the following. We're going to have minus n over 2 times 1 over theta. That's just going to be 0. And then we're going to have minus 1/2 times negative 1 theta to the minus 2 times the sum I equals 1 to n yi minus mu squared. Because notice this term here doesn't have a theta in it, it's just a constant. And then this simplifies to minus n over 2 theta plus 1 over 2 theta squared times the sum I equals 1 to n yi minus mu squared. And again, the next thing we're going to do is we're going to set this equal to 0. So if we do this, we get minus n over 2, and since I'm setting this equal to 0, I'm going to replace my thetas with theta hats. And what I'm going to do is then solve for theta hat. So notice if we do this, we're going to get that 1 over 2 theta hat squared times the sum I equals 1 to n yi minus mu squared is equal to n over 2 theta hat. Now notice if I multiply both sides by a theta hat, the theta hat on this side will cancel with one of the theta hats over here. And so then I would have 1 over 2 theta hat times the sum I equals 1 to n yi minus mu squared is equal to n over 2. Notice these 2's are going to cancel if I multiply both sides by 2. So note what we can do here is this then becomes, if we multiply both sides by theta and divide both sides by n, we would get that theta hat is equal to the sum I equals 1 to n yi minus mu squared divided by n. So now what we can do is we can replace mu with our estimate for mu, which was y bar, and we can replace our theta hat with sigma hat squared, because that's really what theta hat is an estimate for sigma squared, and this gives us the following. But notice, this is not the typical estimator we use for the variance. And so this is not s squared, because remember s squared has an n minus 1. So we get that y bar is the MLE for mu, but the MLE for sigma squared is the estimator that has n, not n minus 1, in the denominator. If you're following along in your book, do go ahead and skip example 9.16. We're not going to work any problems where the range of y depends on theta. And we've got an extra fact here. So if u is any sufficient statistic, then the MLE is always a function of u. Thus, the MLE is a function of the minimal sufficient statistic. So if MLEs are unbiased, then it's going to be MBUE. Also, any function of the MLE is unbiased and will also be MBUE. We also have what's called the invariance property of MLEs. So suppose that theta hat is the MLE for theta. Let t of theta be a function of theta that has a unique inverse. Then t of theta hat will be the MLE for t of theta. And you might ask, well, why is that useful? Well, the reason that's useful is, for example, we just found the MLE for sigma squared. We can use this to help us get the MLE for sigma. So in our previous example, we found that y bar and sigma hat squared, which was equal to the sum I equals 1 to n yi minus y bar squared divided by n, are the MLEs of mu and sigma squared. So let's consider the function t of sigma squared, which is just equal to the square root of sigma squared, which is equal to sigma. Well, notice this function has a unique inverse. Now, usually the square root doesn't have a unique inverse, but it does in this case, since sigma squared, since sigma is strictly greater than 0. We know the standard deviation is always greater than 0 or equal to 0. So what we know is t of sigma hat squared, which is equal to the square root of sigma hat squared, is just equal to sigma hat, which is equal to the square root of the sum I equals 1 to n yi minus mu squared divided by n. We know that this is the MLE for sigma by the invariance property. So this video concludes the notes for section 9.7.